Good morning. Today we'll be talking about the degenerate Cope rearrangement, the topic on fluxional molecules. Now, let's imagine that if we have a reaction in which, following a Cope rearrangement, the reactant and products are similar, exactly the similar reactions. Then this would mean that the energy required for the forward reaction and that required for the backward reaction should be similar. And if that is the case, we can call these kind of Cope rearrangements starting from the reactant to the product and while going back from the product to the reactants as degenerate Cope rearrangements. And if the Cope rearrangements are degenerate or equal in energy in nature, this would mean that the reaction would convert the reactant into product and again convert the product back into reactant. This interconversion will move on rapidly, and if this is happening very quickly within a fraction of second in time, we would say that these molecules show fluxional nature. That is, the interconversion rate is good, then one form rapidly interconverts into the other form, and therefore in those molecules where there are degenerate Cope rearrangements because of the similar nature of the reactant and the product, these kind of Cope rearrangement or degenerate Cope rearrangement molecules show fluxional behavior. That means they are fluxional in nature. Now, as I've told you, if following a Cope rearrangement, the reactants and the products are similar, then the energy requirement for the forward and backward reaction remains the same. And if that is the case, the similar energy interconversions between similar isomeric structures, that means both structures are isomeric, the reactant and the product, produced as the result of Cope rearrangement are called degenerate Cope rearrangements. And the isomers produced will rapidly interconvert between one form to the other, and therefore these molecules are called fluxional molecules. Therefore, fluxionality or the rapid interconversion of isomeric forms following a simple rearrangement should be called as degenerate Cope rearrangement or the concept of fluxional molecules. The simplest example in this regard should be a hexa 159. You know, hexa 159 is the substrate on which a Cope rearrangement occurs. You know what is a Cope rearrangement? That in case of hexa 159 following a 6-membered cyclic transition state, 3,4 bond breaks and 1,6 sigma bond is formed. A 1,2 double bond gets converted into 2,3 and a 5,6 double bond gets converted into the 4,6 double bond. So if I have a simple hexa 159, then the reactant and the product's shape should be exactly similar. Therefore, reactant and products are exactly similar. Therefore, energy required to convert a reactant to a product and the energy required for converting to product to the reactants are equal. Therefore, these two isomeric forms will rapidly interconvert into one another, and if they rapidly interconvert into one another, we'll call these molecules as fluxional molecules. Now, if I have a hexa 159 molecule, the only deterrence or the only problem as far as taking the fluxional behavior is concerned is the rotameric form of the hexa 159. Now we know that if I am to talk about a hexa 159, the better form which is more stable in terms of the conformation of this molecule should be the transoid form. Transoid form is one in which both double bonds are away from one another so as to minimize the electronic repulsions. But we know for a hexa 159 to undergo a Cope rearrangement, a 6-membered cyclic transition state has to follow and a chair-like transition state has to follow. And since a chair-like transition state will be only possible if this molecule assumes a cis-oid conformation. Therefore, speaking in terms of energy, molecules will prefer staying in the transoid form. Some amount of energy would be required to convert the transoid form, which is more stable, to the less stable cis-oid form, and then this cis-oid form, once formed, will get converted into will undergo a Cope rearrangement and get converted into the isomeric product. Now, point is that if the transoid form is more stable, cis-oid form's existence and equilibria would be comparatively very less, and some amount of energy would be required to convert the transoid form into cis-oid form. Therefore, this raises the activation energy barrier and is a deterrence in the way of faster Cope rearrangement. Means Cope rearrangements would be slow because some amount of energy would be required to convert the more stable transoid form into the less stable transoid form. Therefore, the activation barrier, the activation energy required to cross the from reactant of a Cope rearrangement to a product of a Cope rearrangement is higher, and therefore Cope rearrangement is slow. As I've told you, this would mean some energy would be required to convert the trasoid hexa-1,5-diene molecule into the cis-oid form. This raises the activation energy barrier of the Cope rearrangement and therefore reduces the speed of fluxionality shown by these molecules. So what do we need to do? Somehow if we can lock a molecule into the possible cis-oid conformation, this would probably be better for a molecule to undergo Cope rearrangement. And that is where new molecules came into picture, which had a kind of a locked diene, a hexa-1,5-diene locked in a cis-oid conformation. One example of a fluxional molecule in this category is homotropolenine. Homotropolenine fluctuates between its two isomeric cis structures at 1000 times per second when the temperature is raised to 180 degrees Celsius. Let's see first of all what is a homotropolenine molecule. Homotropolenine molecule basically is this molecule. It is a 6-membered ring like this, in which you have two double bonds here and let's say here, and sorry, it has two double bonds here and here, and attached to these two allylic carbon atom is a cyclopropyl ring. This molecule, not this one, the double bonds are here and here. This molecule is a homotropolenine molecule. As you can see, the hexa-1,5-diene 1, 2, 3, 4, 5, 6. Of course, this is not the IUPAC nomenclature. Had it been IUPAC nomenclature, the numbering would have been 1, 2, 3, 4. So it's not IUPAC nomenclature. This is hexa-1,5-diene. It's a part of a cyclic system. Therefore, we have locked the hexa-1,5-diene into a cis-oid conformation. And once it is locked into a cis-oid conformation, no energy is required to convert the transoid more stable form into the cis-oid form, since it is already existing in a cis-oid form. Hence, the activation energy barrier is less. That would mean degenerate Cope rearrangement would be faster. But if you look at the structure of this homotropolenine molecule, you'd find that the 6-membered ring here is this one. The cyclopropyl bridge attached to 3rd and 4th carbon atom, this and this, can assume two configurations. Either this can be around this side, can assume two conformations. Either it can be around this side, that is the 3,4, this cyclopropyl bridge is away from this diene framework, or it is towards the diene framework. If it is away from the diene framework, we call it as trans. Of course, this is a misnomer, not the right way of representing, but anyhow. And if it is towards the diene framework, we call this as the cis isomer. Now, for the Cope rearrangement to occur, for an extensive Cope rearrangement to occur, the molecules undergo Cope rearrangement in this cis-oid form. So this cis-oid form got converted into this. So this is the cis-oid form of homotropolenine. This underwent a Cope rearrangement, produced another cis-oid form of the homotropolenine molecule, and which again, if this is not undergoing Cope rearrangement, it will exist in a more stable trans form, which is there. Now, since we have locked the diene in the cis-oid conformation, the two isomeric cis-oid forms, this cis forms, rapidly interconvert into one another at 1000 times per second at a temperature of 180 degrees Celsius. Now, if you look at this reaction, how will this reaction be possible? It is very simple. If you locate hexa-1,5-diene, this molecule, this is 1, 2, 3, 4, 5, 6, and we know how does this reaction occur? That 1,2 double bond breaks and forms the 2,3 double bond, 3,4 double bond goes in to form the 4,5 double bond, 5,6 double bond breaks and forms the 1,6 single bond. That means the bond will be between here and here. This bond will break. That means we'll end up in this molecule. And once we end up in this molecule, the two cis forms are rapidly interconverting into one another to show fluxional nature. Again, molecule, as you can see in this case, and as I've drawn the signs of the equilibria is largely towards the transoid form because it is sterically more stable. Therefore, some amount of energy definitely needs to be used or needs to be utilized to convert the more stable transoid form into the less stable cis-oid form. Again, this raises the activation energy barrier, and that is why the fluxionality, though it is very good, but it occurs at the elevated temperature because the activation energy barrier is large. Therefore, as I've told you, again, molecule prefers staying in the more stable transform, which reduces the enhanced chances of fluxionality. Now, how can we reduce the transoid form formation and restrict this molecule into the cis-oid form? It is simple. If in this particular molecule, we can join these two ends here, this one and this one, then the molecule will be locked in a cis-oid form, and if it is locked in a cis-oid form, definitely the degenerate Cope rearrangements energy barrier would be small. That means the activation energy barrier would be small, and then you can expect that this molecule would be fluctuating very fast into one another. And there are three particular examples in this particular group, and as I've told you, joining the methylene bridge, which methylene flap? This methylene flap of cyclopropane bridge, this one, with the cyclohexadine's methylene, this one, reduces or eliminates the formation of the trans isomer and locks the molecule into the more reactive cis form. And there are three examples of this particular homotroponidine molecule, as you can see. If you can straight away by a carbon-carbon single bond join these two carbon atoms, then the molecule which we get is called semi-Bullvalene. If you have one CH2 bridge between them, it is called Bullvalene. But if you have a vinyl bridge, a CH double bond CH between these two molecules, this is called Bullvalene molecule. And it is this Bullvalene molecule which is perhaps the best example of fluxional molecules which arise due to the degenerate Cope rearrangement. Let's try to work out and understand this Bullvalene molecule. As I've told you, Bullvalene molecule is probably one of the best examples of fluxionality because of the degenerate Cope rearrangement. Now, if you look at this molecule properly and closely, you'll observe that this molecule has a threefold axis of symmetry. There are three equivalent Cope rearrangements are possible in each structure which are identical. Now, as I've written the Bullvalene molecule, you can see that this is the Bullvalene molecule, and if you find this Bullvalene molecule, you find that this is one hexadiene, this one is the second hexadiene, and this one is the third hexadiene. Repeat, this and this double bond forms the one hexadiene, this and this double bond forms the second hexadiene, and this and this double bond forms the third hexadiene. Therefore, as I've told you, this particular molecule has three equivalent Cope rearrangements possible in its structure. There are 10 CH bonds in the molecule which can occupy any of the 10 positions in the molecule. This is very important. If you work out this molecule properly, as I've written in this particular case, this is the Bullvalene molecule. I've written it in or rearranged it in this fashion. There are in fact three hexadiene molecules. One is between this and this, another one is between this, and the third one is between this and this. If you look at this entire structure and you work out, that you'll find that there are 10 CH groups in the molecule. This carbon at the 7th is having one hydrogen atom, at 6th is 1, 5th is 1, 4th is 1, 3rd is 1, 2nd is 1, then 1 has one hydrogen atom, this 10th has 1, 9th has 1, 8th has 1. So in total number of carbon atoms in this system have 10, and each carbon atom is methine in nature, is CH in nature. That means it has 10 CH bonds. And beauty of this molecule is that because of its fluxional nature, because of its rapid interconversion into the isomeric forms, each of the 10 carbon atoms occupy each other's position. They rapidly interconvert into one another. In fact, and because of which there are 10 factorial divided by 3, that is 12,09,600 identical structures or isomers which are possible for Bullvalene molecule. This is a big number. That means Bullvalene molecule can interconvert into one another and create 12,09,600 isomeric structures. Now, as I've written here, Bullvalene fluctuates at about 4,000 times per second. This is the speed of fluxionality at, importantly, room temperature. If you remember the case of homotroponidine, it converted into its isomeric forms at 1000 times per second, but at elevated temperature of 180 degrees Celsius. In the case of Bullvalene, the interconversions are much rapid at 4000 times per second, and importantly, it occurs at a lower activation energy barrier, and therefore room temperature is sufficient to bring about this degenerate Cope rearrangement. And the best part about this thing is even the NMR machine is not able to determine the different types of protons in this thing. All 10 protons here in the case of Bullvalene molecule appear to be identical, and in the NMR spectrum we get only a singlet at delta value 4.22 corresponding to the NMR, even if the NMR is taken at 100 degrees Celsius. What I'm trying to say here is, if you look at this Bullvalene molecule, you'd find that 1, 2 protons, proton at 8 and 9, proton at 6 and 7 are all olefinic protons, so they should be coming downfield, whereas 7, 4, 3 and 10 are methyne protons and they should be coming upfield. Why are they coming as a singlet? That means the interconversion is so fast that third proton after interconversion or after a Cope rearrangement will become second, and second will become third, 1 will become 9, 10 will become 4 and so on. That means the interconversion is so fast that the machine or the NMR spectrum is not able to identify which proton we are considering. Therefore, it records all protons at a single value at a delta value of 4.22, which goes to show that the interconversion process is extremely rapid. Now let me try to draw all three degenerate rearrangements considering all three diene systems. Okay, we'll start with first of all hexa 1,5 diene, in which I've taken the diene system between this and this double bond. If it is a hexa 1,5 diene, I need to locate a 1,5 diene into this. So if you find or follow the numbering, this is 1. As with all hexa 1,5 dienes, we start the numbering by the terminal position of a double bond. Let's say this is 1, 2, 3, 4, 5 and 6. So it is 1,5 hexadiene. Now, as you know, in Cope rearrangement, what happens? 1,2 bond breaks and forms a 1,6 bond. 5,6 bond breaks and forms a 4,5 bond. 3,4 bond breaks and forms a 2,3 double bond. This is what happens. And all I've done from this to this, I've written this thing only. I've broken this bond, drawn this bond. I've broken this bond and drawn this bond. I've broken this bond and drawn this bond. Right? I've retained the numbering from the reactant to the product. You can see what was the numbering in the reactant, the same is the numbering in the product. Now if you find or look at this molecule and if you follow the numbering, look at this ring system here between 1, 2, 3, 10, 9, 8, 7, 6, 5, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's a 10 carbon atom ring, as you can see. If you follow this numbering in such a way that, let's say we are numbering it in such a way that this portion of the ring, follow the ring numbering from here. Let's say, as you can see, 6, 7 is the one in which I'm having a cyclopropyl bridge. So I'll keep 6, 7 wala part outside. So I'm taking this portion as the ring structure. So I have 1, 2, 3, 10, 4, 5, 6, 7 as the main ring. 1, 2, 3. I'm sorry, not 1, 2, 3, 4. I'll take this part of the ring. 6, 7, 5, 4, 10, 9, 8, 7 as one ring. So it is how many carbon atoms? 1, 2, 3, 4, 5, 6, 7. So it's a 7 carbon atom system. I'll draw the 7 carbon atom system ring like this. I'll retain the numbering at 6, 7 carbon atom. I've kept it here because here it is the cyclopropyl bridge. Attached to 6 is 5, attached to 5 is 4, and between them is a double bond. Attached to 4 is 10, attached to 10 is 3, attached to 10 is 9, attached to 9 is 8, attached to 8 is 7. So I've made the outer ring. What is left is the inner ring. You can see attached to 10 here is third atom, so 3. Attached to 3 is 2, attached to 2 is 1 is here, and 1 is attached to further 6, 7. So as you can see, starting from the reactant to the product, we've ended up in a similar kind of a structure. That means going from here to here and converting from here to here would require the same energy. So Bullvalene molecule is interconverting into one another. And see, the 10th carbon atom, which was earlier methine in nature, or you can see the 9th or 8th, you can see this 10th carbon atom, which was earlier methine, is now 1. The 4th carbon atom is now 6. The 5th carbon atom is now 5th only. For second is 8th, 1 is 9th. Therefore, there is a rapid interconversion between the carbon atoms here. Similarly, let's look at the second hexa 1,5 diene. Earlier we have taken this and this double bond. Let's now take this and this double bond as a hexa 1,5 diene system. Is it a hexa 1,5 diene system? In order to understand this thing, I have to locate that hexa 1,5 diene. So it is 1, 2, 3, 4, 5, 6 is hexa 1,5 diene. I'll continue numbering. Let's say after 6 is 7, 8, 9 and 10. Right? Again, the logic is same. 5, 6 bond breaks and forms a 1, 6 bond. 1, 2 bond breaks and forms the 2, 3 bond. 3, 4 bond breaks and forms the 4, 5 bond. So if I retain this kind of a thing, what has happened is the outer structure remains same. Inner portion, this bond breaks and forms a double bond between 4 and 5. 5, 6 double bond breaks and forms a bond between 1 and 6. 1, 2 double bond breaks and forms this thing. So if you write this molecule in this fashion, the only thing I've done is I've rotated this molecule upside down and we end up in this structure. So again, we have ended up a similar structure following the second Bullvalene rearrangement, second degenerate Cope rearrangement. And third molecule is between this and this. Again, locate 1,5-hexadiene, 1, 2, 3, 4, 5, 6. This is 7, 8, 9, 10. Again, 1, 6, 5, 6 bond breaks, forms a bond between 1 and 6. 1, 2 bond breaks, forms a bond between 2 and 3. 3, 4 bond breaks, forms a bond between 4 and 5. Is this structure? Try to write the structure in a proper fashion. Again, the molecules are similar in nature. That would mean that these molecules are rapidly interconverting into one another following a Cope rearrangement, since the structure or the shapes of the reactant and the products are similar. Therefore, the rearrangement would require similar energy from going in the forward direction and from coming in the while coming to the backward direction. Hence, the Cope rearrangements are degenerate, and since they are degenerate, they are rapidly interconverting into one another. And as I've told you, Bullvalenes is a supreme example of a degenerate Cope rearrangements. So this is it with degenerate Cope rearrangement. Now we'll be talking about a very important reaction called Ene reaction. Ene reaction is also called Ene reaction. It's basically a concerted pericyclic reaction which occurs between an alkene. An alkene can be a simple alkene, that means a carbon-carbon double bond containing species. It can be an alkyne, that means a carbon-carbon triple bond containing species. It can be an arene, that means an aromatic system can be there. It can be a alene, that means a carbon double bond carbon systems will be there. But all the systems necessarily should have an alpha hydrogen present in it. And once it has an alpha carbon atom, for example, if it's a simple alkene, attached to the alpha carbon atom is a hydrogen, that means we are talking about the allylic hydrogen atom. So in the case of simple alkenes, all those alkenes which have allylic hydrogen atom, which we call in the Ene reaction as the Ene component, reacts with another multiple bond, another alkene species, which can be a simple alkene, a carbon-carbon double bond species, a carbon double bond oxygen, or a carbon double bond nitrogen species, which we call as the one attracted to the ene called the enophile. So we have two components here. One is an ene. What is an ene? Ene is any alkene which has an allylic hydrogen atom, and the second component can be a simple carbon-carbon double bond or alkene, or a carbon-oxygen double bond, a carbonyl group, or carbon-nitrogen double bond, etc., which the second component we call as an enophile. And the result is that these two components react in such a way that a new sigma bond is formed with the migration of a double bond, and we witness a 1,5 hydrogen shift in this reaction. If that is the case, we call these reactions as Ene reactions. Now, the result of this Ene reaction is that the product obtained is a substituted double bond shifted to the allylic position. So what I'm trying to say, I'll try to explain this with the help of the reaction or the picture. Two components. One is an ene. What is an ene? You should have a double bond system, a triple bond, an aromatic system, an arene system, or any system which has attached to its alpha carbon atom a hydrogen atom. So we have an ene. Ene can be, as I've told you, can be an alkene, can be an alkyne, can be an alkene, alene, can be an arene, or a CS, carbon heteroatom bond system. But all the systems should have an alpha hydrogen atom. Alpha hydrogen atom should be present in those systems. And the second component of the Ene reaction is called the enophile, of course, which is attracted to the ene. It can be a simple carbon-carbon double bond, or it can be a carbonyl system, carbon double bond nitrogen, carbon double bond sulfur, or an oxygen system, nitrogen systems, or even the carbon triple bond carbon systems. The reaction occurs in such a way that if you look at or move the arrows between this thing, what happens is overall, if you see, it's a intermolecular. Between two molecules, there is a sigmatropic rearrangement. If you work through the sigmatropic notations, you'd say that this bond breaks. Hydrogen attached to the allylic carbon atom. That was, if you remember, we used to talk about sigmatropic reactions in such a way that it is the allylic sigma bonded group which migrates over the pi framework. So this is the double bond attached to the carbon atom is the allylic group. Attached to the allylic group is the hydrogen atom. So hydrogen is migrating. If this is hydrogen is 1, 1, it migrates to 2, 3. Now this is one molecule. But in the case of simple sigmatropic shifts, the fourth and fifth carbon atoms were the part of a ring only, of the part of that single structure only, single molecule only. But in the case of Ene reaction, the fourth and fifth carbon atom, or fourth or fifth atoms, are not a part of a ring, they are different molecules. And then if so happens that this hydrogen atom from 1 migrates to 5th position, so what will happen? This double bond breaks and picks up this hydrogen here. This hydrogen bond breaks, forms a double bond here. This bond breaks and forms a carbon-carbon bond between this 3 and 4th carbon atom. The result is, as you can see with the help of the transition state, this bond is forming between this and this. This bond is breaking. This bond, double bond is forming. This double bond is breaking. This single bond is forming. So this reaction proceeds through a 6-membered cyclic transition state, and the result is, as you can see from the arrows, the hydrogen migrate from the 1st position to the 5th position, and the double bond migrates from the 2nd, 3rd position to the 1 and 2 position. That is what we said. A new sigma bond is formed. A new sigma bond is formed. Then we said with the migration of the double bond, earlier the double bond was here. Now in the product the double bond is here. So migration of double bond, and there is a 1,5 hydrogen shift. That is what is an ene reaction. Now as you can see, ene reactions are intermolecular 1,5 hydrogen shifts, 1,5 hydrogen sigmatropic shifts. So we can call these reactions as group transfer reactions in pericyclic chemistry. So ene reaction is an example of group transfer pericyclic reaction where an entire group is transferred from one molecule to the other, which usually has high activation energy barriers because you're transferring one group to other. Normally the amount of energy required would be high, therefore the activation energy barrier is high, and therefore would require elevated temperatures or activated substrates to conceive the reaction. That means we need either to have higher temperatures, or my reactant subsystems, that is either the ene or the enophile, should be such that are activated in nature so that the energy gaps are small and so that their perturbation is large, so that their reactivity is faster, and then possibly the reaction will occur at lower temperature. Otherwise, normally speaking, ene reactions, because they require higher activation energy barriers, would occur at elevated temperatures. Ene reaction should be represented as like this. If you figure out this thing, this system has this double bond which is involved in this reaction, and this carbon hydrogen single bond in which is involved in this reaction. So this component is contributing 4 electrons. This component is contributing 2 electrons. Therefore, it should be a kind of a 4+2 cycloaddition reaction. But this is not a cycloaddition reaction because these 4 electrons are not all pi in nature. Therefore, I can say 2 pi electrons here, 2 sigma electrons here, and 2 pi electrons here are undergoing some kind of a reaction. And since the default stereochemical mode, as in all cycloaddition reactions, is supra-supra, therefore I can designate this reaction. If you remember, I used to designate a simple 4 plus 2 as pi 4 plus pi 2. But since here first component, that is the ene component, does not have all 4 pi electrons, it has 2 pi electrons and 2 sigma electrons. This component has 2 pi electron, the enophile. Therefore I can call this reaction as pi 2 supra, sigma 2 supra, and pi 2 supra sigmatropic reaction. Call it as sigma 2 supra and sigma 2 supra corresponding to the ene, and sigma 2 supra corresponding to the enophile. So I can categorize or designate the reaction, ene reaction, in this way. So if I repeat again, ene reaction is a reaction which occurs between two components. First component is an ene. What is an ene? Ene should be any multiple bonded system which should have an alpha hydrogen atom. And the second component is an enophile. Enophile can be any simple carbon-carbon system, carbon-carbon double bond system, or it can be any carbon-oxygen, carbon-nitrogen, carbon-sulfur, oxygen-oxygen, any system which should have a double bond. What will happen in the reaction? Through a 6-membered cyclic transition state, this double bond will migrate, or this hydrogen will migrate from the 1st position to the 5th position. This double bond will shift from here to here, and there will be a single bond formation between these two. This overall reaction is called ene reaction, or is simply called the Elder-Ene reaction. Now let's look at the two components involved. The first component, as I've told you, is the ene component. What is an ene component? As I've told you, it should have a pi bond which containing reactant. There should be a minimum 1 pi bond, and it should have an active hydrogen atom present at its alpha position. So various systems can be an allylic system. Allylic system is what? A double bond attached to the allylic carbon atom is a hydrogen atom. Therefore, it is allylic. It can be propargylic. What is a propargylic system? The difference between allylic and propargylic is, in allylic system you have carbon-carbon double bond. In propargylic system you have carbon-carbon triple bond. Attached to the next carbon atom is a hydrogen. So it's propargylic. In allenes, carbon double bond, carbon double bond, carbon attached to the next carbon, that is the alpha carbon, you should have a active or a hydrogen atom. Cyclopropyl ring. attached to the next carbon atom, that is the alpha carbon, is hydrogen. Now this cyclopropyl ring does not have a double bond. Why should we consider cyclopropyl ring as an ene component? Is because all cyclopropyl systems are considered to be isomeric with the chain form. You must be knowing regarding the ring chain isomerism, and if you know about this thing, we say simple propene molecule and cyclopropyl systems are isomeric with one another. Therefore, this strained molecule acts as a double bond system, and if it is a double bonded system in a strained manner, this hydrogen, this alpha hydrogen, can be acting as the ene component, right? Again, aromatic systems also, if you look at the aromatic systems attached to the benzylic carbon atom, that is the next carbon atom attached to the benzene ring, you have this hydrogen atom. So you have benzylic hydrogen atom. This can also act as an ene component. Interestingly, phenols have this double bond. Attached to the next carbon atom or attached to the next atom, which is the allylic atom, you have the hydrogen atom. So this system can also participate as a ene component. This occurs, but it occurs normally. Phenols acting as enes in ene reaction are very, very rare, and it requires a lot of elevated temperature to conceive this reaction. Other systems acting as enes can be any carbon heteroatom double bond, which can be carbon oxygen, carbon nitrogen, or carbon sulfur. But again, these systems, examples of ene reaction, ene component using this carbonyl systems or carbon heteroatom systems are rare. The larger or the simplest examples in which the ene component is using is the allylic, propergillic systems, which is normal examples in which acts as the ene component. So ene component is a pi bond containing reactant which has the alpha hydrogen atom in it. The second component, which we call it as an enophile, which is attracted to the ene. Any system which is attracted to ene should be enophile. Again, it should be a pi bonded system or a substrate that are attracted to the ene component, and therefore they are called enophiles. So what kind of systems can act as enophile? As I've told you, simple carbon-carbon double bond as in ethene, some acetylene molecules as in ethine, some benzynes. So carbon-carbon multiple bond containing systems can act as enophile. Also, carbon oxygen double bond, very common ene reactions occurs in carbon oxygen double bond acting as enophile. These reactions we call it as carbonyl ene reactions, to be particular, when enophiles are carbonyl groups. These are very common in literature. Then carbon nitrogen double bond can act as an enophile, carbon double bond sulfur, or even carbon phosphorus bonds can act as enophiles. Then heteroatomic systems like nitrogen, oxygen, silicon, NO, and S double bond O can also act as enophile. Then cumene systems or cumulene systems in which you have nitrogen, sulfur, oxygen double bonds, nitrogen double bond, sulfur double bond, nitrogen, carbon double bond, oxygen, or carbon double bond, sulfur, and even sulfur dioxide can act as enophiles. Even there are certain examples in literature where your charge systems like C double bond N positive, C double bond S positive, or C double bond O positive, and even C double bond some metal positive charge is also possible to act as an enophile. The most common enophiles are ones which are either carbon-carbon double bonds. They normally require higher temperatures, but if you have carbon heteroatom double bonds, these are more common enophiles in the ene reaction. Now let's try to understand the reaction conditions under which this ene reaction is possible. We start with the FMO approach to explain the reaction condition. As you know, FMO approach believes that the major contributing interaction, and which normally is the homo-lumo interaction, is the deciding interaction which controls the reaction conditions. Therefore, if in the homo-lumo interaction, considering a particular stereochemical mode, which normally under default cyclodation reaction is supra-supra, and if we assume that it is supra-supra cyclodation in the case of ene reaction also, so if in supra-supra addition, if the bonding interaction is achieved at both the reacting ends of the system, then probably this reaction would be thermally loud. If it is not the case, we look at the excited state. If in the excited state there are bonding interactions, then this process would be thermally loud, otherwise forbidden. Now, let's look at this thing. Like in a normal Diels-Alder cyclodation reaction, as I've told you, the Diels-Alder cyclodation reactions under the rate of cyclodation category, we've said that there are three possible types of Diels-Alder cyclodation reaction: type 1, type 2, and type 3. Type 1, which is also called the normal Diels-Alder cyclonation reaction, is one in which you have HOMO of the diene placed at higher energy than HOMO of the dienophile, and by virtue of this, the HOMO of the diene and LUMO of the dienophile is the most important interaction, and any substitution pattern on this interactive systems would alter the speed of the reaction. Similarly, in the Ene reaction also, it is the HOMO of the Ene system and LUMO of the enophile which is the major and the most important contributing interaction in terms of energy. Therefore, any substitution pattern which could probably reduce the energy gap between the HOMO of the Ene and LUMO of the enophile could probably speed up the reaction, and any substitution pattern which could probably increase the energy gap between HOMO of the Ene and LUMO of the enophile could probably retard the speed of the reaction. Now, in order to consider the FMO approach, let's look at the system in such a way that we know Ene is a 1 pi bond system and has one CH bond system which are involved. As I've told you, the Ene component has one double bond and one CH bond which is involved in the reaction. Therefore, it is a 4 electron system, and if it is a 4 electron system, my HOMO should be psi 2. So for me it is simple. If I'm going to draw the HOMO corresponding to this system, I'll be drawing three p lobes. Hydrogen is of course having the sigma, having the circular, the spherical shape. Now in this psi 2 is one node. There should be one node. If one node is there, it should be here in the center, considering this is a 3 carbon atom system. If this is positive, one node, then with this would be negative. If this sign is negative, hydrogen will of course have the similar sign only, right? So this is the HOMO of the Ene. Regarding the LUMO of the enophile, enophile is a carbon double bond carbon system, simple, a 2 electron system. So 2 molecular orbitals are permissible. One is pi 1, another one is pi 2 star, and pi 2 star is LUMO, which has one node. One node means if this has positive sign, this will have negative sign. So if you look at the interactions which are possible between the terminal ends of the Ene and terminal ends of the enophile, since hydrogen is getting detached from this atom and getting attached to this atom, therefore as you can see, there are bonding interaction between this and this and between this and this. So it is allowed under this portion of the molecule, and here also positive is interacting with positive. That means both components have bonding interaction, and therefore since we have not excited the molecule, we are considering only the thermal conditions. We can say that HOMO-LUMO interactions are bonding in nature, therefore this reaction is thermally loud. Hence Ene reactions according to the FMO approach are thermally loud. I'll repeat again how we have taken HOMO. With HOMO is psi 2 because this system is a total 4 electron system. So 4 electron system psi 2, there are 3 carbon atoms. I have to draw a lobe like this. This is the negative sign because here it is negative. You can see if here to here is bonding, here to here is bonding, here and here is bonding. Since we have bonding interaction between all components which are actually interacting, therefore this reaction is allowed. And since we have not excited the molecule, we are only considering the ground state, we'd say this reaction is thermally loud. So this is the FMO approach on the basis of which we can say that Ene reactions are thermally loud. We can also take the aid of the PMO approach, and as you know, in all PMO approaches, we only draw or consider the most stable molecular orbital, and we then draw the cyclic transition state leading from the reactant to the product. Again, as I've told before, Ene reaction proceeds through a 6-membered cyclic transition state. So if I depict that 6-membered cyclic transition state, the most stable orbital is this one, corresponding to the Ene, and corresponding to the enophile is this one. So if you look at here, and of course I'm considering which interaction, supra. This component is interacting, the upper lobes of the enophile and the lower lobes of the Ene are interacting. So suprafacial corresponding to Ene and suprafacial corresponding to enophile. As you can see with the interaction, positive is in this total system. This has 4 electrons, this has 2 electrons, so number of electrons are 6. So it's a 6 electron system. Number of nodes are, as you can see, 0. Stereochemical mode of course is supra. 6 electron system with 0 node follows Huckel's rule, therefore is aromatic, and according to PM approach, aromatic systems are thermally loud and anti-aromatic systems are photochemically loud. Since this reaction is aromatic under thermal conditions, therefore this we can say, considering the PM approach, that the reactions are thermally loud. So we can say safely that Ene reactions are thermally loud reactions. Let's talk about the reactivity using the Ene reaction. As I've told you, it is the HOMO of the ene and LUMO of the enophile which is the major interaction, the most contributing interaction. And since it is the most contributing interactions in terms of energy, therefore any substitution pattern that could probably lower their gap should speed up the reaction, and that could probably increase their gap should retard the reaction. And we know if you want to lower the HOMO-LUMO energy gap between ene and enophile, I need to raise HOMO above in energy and I need to lower LUMO below in energy level. So if I have to raise LUMO, HOMO of the ene, I have to substitute ene with electron donor groups, and if I want to lower the LUMO of enophile, I have to substitute this with an electron withdrawing groups. Or I could probably change my enophile from an all carbon enophile to a carbon heteroatom enophile. Now replacing an heteroatom instead of carbon atom in the enophile would bring in an electronegative atom, and bringing in an electronegative atom will try to suck in the electron density from that system, lower its energy, and would make the energy gap between the HOMO and LUMO smaller, and probably would intensify or speed up this reaction. Hence, carbonyl ene systems, as if I read these lines again, since HOMO, ene and LUMO enophile are the major interaction, therefore electron withdrawing substitutions on enophile or replacing the carbon atom of the enophile with an electronegative heteroatom lowers the energy of LUMO. This reduces the HOMO-LUMO energy gap and speeds up the reaction. Hence, the carbonyl ene reactions in particular, C double bond O, where the enophile is C double bond O, having enophile as CO group, are faster and requires lower temperature to conceive this reaction. So they are better components in the ene reaction than the carbon-carbon, all-carbon-carbon double bonds. We'll talk about one variant of the ene reaction. Rather than two systems, that is the ene and enophile being a part of two different molecules, there is possibility that ene and enophile are a part of a simple or a single molecule. If that is the case, we'll call these ene reactions as intramolecular ene reactions. Therefore, intramolecular ene reactions are one in which ene and enophile are a part of a single molecule. Therefore, less negative entropies are involved, which means that intramolecular reaction should be more facile than the intermolecular counterparts. What does it mean? Now, in order to react, the two components have to come and collide with one another, and this would require some energy. Also, once we bring in the two systems close to one another, we will be decreasing the entropy, and if the entropy decreases according to the Gibbs-Helmholtz free energy concept, if the entropy becomes negative, the chances of feasibility of the reaction, if the entropy becomes negative, the chances of feasibility of the reaction lowers. That would mean that if a system is already in a state where the entropy will not be reduced because we are bringing in the molecules close. Since the molecules are a part of a single system, therefore we are not talking about a system in which lowering of entropy will take place. Hence, these reactions would be more feasible and would be more faster in nature as compared to those ene reactions in which ene and enophiles are a part of different molecule, that is the intermolecular components. Also, simple enophiles such as the unactivated alkenes or alkynes also actively participate in the intramolecular version. As I've told you, those enophiles which are substituted with electron withdrawing groups, or those enophiles in which the carbon atom is replaced by heteroatoms, are better components in the ene reaction. The intramolecular version sees that even the carbon-carbon double bonds react efficiently, because here we will not be wasting energy by bringing in the molecules to collide. That means we are not wasting the transition or the kinetic energy. We are not wasting the entropy concentrations also. Therefore, even the carbon-carbon double bond becomes effective partners in these ene reactions. So depending upon, and finally in the intramolecular version, there are four types of intramolecular ene reaction depending upon the tethering point between ene and enophile. That is the point of attachment where the ene and enophile are joining one another. So depending upon the point of attachment of the tether is the point where they are connected. Between connecting the ene and enophile, the intramolecular ene reaction has been classified by this Upplauser, the name of the scientist. Of course, you have done this work by Upplauser into three categories: type 1, type 2, and type 3. And type 4 is given by Snyder, the fourth category of the ene reaction. We'll be brushing this topic very fast. The four variants are listed here. Let's say this is my intramolecular version of the ene reaction. This portion, enophile, This portion is a double bond attached to the next carbon atom is an allylic hydrogen atom, though this is ene. So I have enophile ene. The enophile's terminal carbon atom takes this hydrogen. This bond breaks and forms a double bond here. This double bond breaks and forms a bond here. So I'll have a bond between this and this. Y takes up a hydrogen and ultimately this product is formed. Second portion is if this double bond of the polyene system is adding in such a way that this XY bond takes up this hydrogen. So rather than this double bond being the part of the system, this double bond is exocyclic in nature. So the point of tethering will break. The similarity will be Y would be taking up the hydrogen. The double hydrogen carbon bond will break and form a double bond here. This bond will break and form a bond between X and Y because it will form a 6-membered ring. So my product is this one. So the point of tether or the point of attachment, as you can see, has varied in these systems. Also, if the allylic hydrogen atom is not towards the end, it is towards the center, then probably a different pathway will be followed. As you can see, X will be now not Y, but X will be taking up this hydrogen, 1,5 sigma tropic shift. So X will take up the hydrogen. XY double bond will break and will form a bond between Y and this carbon atom. This double bond will break and form a bond between this and this carbon atom. So I have a double bond. So I have a 9 carbon atom system. As you can see, there's no bond here. This is by mistake I've drawn. This is X. This is H. So this is this system actually. This is X and there's a hydrogen. It is this system. And finally, if this double bond is here and you have two double bonds attached to here, the point of tether will again change. It is this system which is the ene. This is the enophile. Enophile's double bond will abstract the hydrogen. This bond will move here. It will form a bond between this and this, leading to the formation of the 6-membered ring. So depending upon the substrate and depending upon the tethering point, the joining point between ene and enophile, the ene reactions, the intramolecular version of ene reaction are classified into 4 types. Now we'll talk about certain examples of ene reaction. We'll start with very simple examples. For example, a reaction between, if you consider the first reaction, this is the reaction between a propene molecule and malic anhydride. If you look at this reaction, or if you follow this reaction simply, we'd say that what happens, this component is the ene component, this is the enophile component, and as you can see, enophile's double bond picks up this hydrogen, or hydrogen migrates from this carbon atom to this carbon atom. This bond moves here, this bond forms here, and ultimately we end up in this product. Similarly, let's start with this molecule and let's take this molecule. Now as you can see, this molecule is the ene component because it has the allylic hydrogen atom. It does not have an allylic hydrogen atom. This can only act as an enophile. This enophile is attracted or attached to an electron withdrawing group. Since it is electron withdrawing group, it will lower the energy of the HOMO and will facilitate the ene reaction between the two. How would the ene reaction take place? Again, this hydrogen will migrate to the terminal position of the double bond. This hydrogen, this bond will break and form a bond between this and this carbon atom. This bond will break and form a bond here. So it'll end up in this system. The third example is the carbonyl ene reaction, similar reaction. Again, you can see there is a carbon oxygen bond which is acting as an enophile. We have an ene system. Again, hydrogen migrates. Oxygen, the terminal end of the enophile system, picks up the hydrogen. This hydrogen bond breaks and forms a double bond here. This double bond breaks and forms a sigma bond between this and this. So end up in this product. Let's take a comparatively comparatively difficult example here. Not difficult, but since it proceeds through two processes. How is this product from this product, this reactant? As you can see, this reactant, I have this double bond. This has a deuterium atom. This has a carbonyl group. I cannot find in this particular system which should be ene and which should be enophile. To understand this system properly, let me draw this molecule again in this fashion, let's say. Okay, so this is my molecule. As you can see here, that there's a possibility that this deuterium can be enolized to this oxygen atom, which is simple. They can be keto-enol tautomerism, which is always possible. So deuterium will migrate from this carbon atom to oxygen. So this enolization process will create this kind of an allyne system. Now you see, this kind of an allyl system. So double bond attached to oxygen is a hydrogen atom or a deuterium, its isotopic form. So this is the ene system. There is an enophile which is present internally in the molecule. As you can see this form, there can be two possibilities of enolization. That means this methyl here, this should be methyl, I'm sorry, this methyl here can occupy or this double bond can have two geometrical forms. Either the methyl, this phenyl is this side and OD group is here, that is the larger of the two. This group is larger, the larger of the two, this group is larger. Two larger groups are on the same side, that means it has cis or Z geometry, or the two larger groups can be on the opposite side, that is the trans form. It is the trans or the E form of the molecule which should be more reactive. Now since here the deuterium is here, this is the double bond, this is the enophile component, this is the ene component, this 6th carbon atom takes up this deuterium, this bond breaks here, this bond breaks, 1 and 5th carbon atom joins. So if 1 and 5th carbon atom joins, you'll end up in a 5-membered ring. As you can see, 1, 2, 3, 4, 5, 1 and 5 joins. 6 carbon atoms takes up deuterium, so is CH2. Attached to the first carbon atom is a methyl group, attached to the first carbon atom is a COPH group. So this is my product. And let's talk about the last example, an example in which I'm using the Lewis acid catalysis to conceive this reaction. Lewis acid catalysis probably would increase the speed of the reaction, and this is more predominant in the case of those systems in which the enophile should be one in which you should have a heteroatom system. That means either a carbonyl group or a C double bond N is acting as an enophile. Particularly in carbonyl groups where C double bond O is acting as an enophile, the oxygen, carbonyl oxygen, is electron rich in nature, and therefore it can coordinate with an electron deficient Lewis acid, and this could probably is as if we are attaching a carbonyl group with electron withdrawing group, and if we are attaching a carbonyl group with electron withdrawing group, we are further lowering its energy, further lowering the energy of its LUMO, further decreasing the gap between the HOMO of the ene and LUMO of the enophile, and once the gap is reduced or is lowered, this would probably further speed up the reaction. Therefore, Lewis acid catalysis probably in the case of carbonyl ene reaction further speeds up the reaction towards the formation of more facile product. Now let's take the example of R-citronidal in this case. As you can see, you have a carbonyl group here. Once you take zinc bromide as a Lewis acid, zinc bromide is a Lewis acid, zinc is electron deficient in nature here, zinc is 2 positive, electron deficient, so it will coordinate with this oxygen here, lowering the energy of the carbonyl group. That means lowering the energy of its LUMO, making it as a better enophile component in the ene reaction. So as I've said, Lewis acid catalysis further speeds up the reaction as it coordinates with the carbonyl oxygen. Carbonyl group acts as an enophile and lowers its LUMO on the energy axis, and therefore catalyzes the ene reaction. And if you look at from the reactant to the product, then as you can see here, the OH group is above the plane and it has a similar geometrical relation with respect to methyl group, and this isopropenyl group is below the plane. How have we achieved this stereochemistry going from the reactant to the product? Now to answer this stereochemistry part of the question, the stereochemistry of the OH group, or for that matter the isopropenyl group, could be explained on the basis of the concertedness this reaction undergoes. Let's try to explain this reaction using the proper diagrammatic explanation. Let's say I start with this molecule, the R-citronidal molecule. There's a Lewis acid in it. The Lewis acid is coordinates with this lone pair and oxygen atom here, and there's a coordination of the oxygen and zinc atom. As I've told you, this lowers the energy of the LUMO, makes the reaction more faster or facile. Now if I have to write this molecule here in such a way that I'm trying to draw it in the form in which the zinc is coordinated. Now try to find, let's try to number the system. Let's try to number the system in all possible ways. Let's start with oxygen with 1 number. This is 2nd, 3rd, 4th, 5th, 6th, 7th, 8th. Let's say this is 9th carbon atom to which the allylic hydrogen is attached, and this is the 10th carbon atom. Now I've purposely written in such a way so that I can show a chair-like transition state, chair-like 6-membered transition state while the 1,5 sigmatropic hydrogen shift takes place, that is the ene reaction takes place. Let's try to draw this molecule so that this oxygen is here. So this is first atom, this is 2nd, 3rd, 4th, 5th, 6th, 7th. As you can see, the methyl on the 4th position is above the plane, so we have drawn it in an axial, in the equatorial form here above the plane. Attached to 7th is this 10th carbon atom, and attached to 7th is this 9th carbon atom. As you can see, this 9th hydrogen atom, which will be actually involved in the ene reaction, is this one. So you have a double bond here. As you can see, 9th carbon atom is this is oxygen atom. So if you follow from here to here, this is 1, 2, 3, 4, methyl is above the plane, 5, 6, 7, 8. This is the appearance of this molecule. Oxygen here has coordinated with zinc bromide or the Lewis acid. This is my structure. Now this molecule should have a conformation in which this carbonyl group should be attracting or should be adding on to this hydrogen atom here. So I have two possible orientations. If you follow from here to here, as you can see, what will happen? The oxygen can have two orientations. Either it can occupy because this is a single bond, it can rotate. It can either have the equatorial conformation or it can have the axial conformation. If it has the equatorial conformation, then only it can abstract this hydrogen following the 6-membered cyclic transition state. If it was having the axial conformation, then probably that 6-membered cyclic transition state in a chair conformation would not have been achieved. Therefore, the molecule orients itself or locks itself in such a conformation where this oxygen moves above the plane, that is the equatorial position. Okay, once it achieves the equatorial position, oxygen will abstract this hydrogen through this 6-membered cyclic transition state. This bond will break. This bond will start breaking. Form a double bond between 8 and 9. Form a double bond between 8 and 9. This double bond will start breaking between 7 and 8. It will start breaking. Bond between 7 and 2 will be formed. Bond between 2 and 1 will be breaking in nature. So I have a 6-membered cyclic transition state through which the abstraction takes place. So Ene reaction, as I've written, occurring through a 6-membered cyclic transition state where the oxygen atom at C2 assumes the equatorial position because it has to abstract the hydrogen in a cyclic 6-membered chair-like transition state. So if that is the case, what will happen from here to the product? There will be a bond formation between 2 and 7. There will be a single bond between 7 and 8. 8 and 9 will assume a double bond character. Oxygen will have this hydrogen atom abstracted and will have OH. And as you can see, the position of the OH and the position of the methyl, OH is equatorial above the plane, methyl is equatorial above the plane. Both are above the plane. Therefore, if I have to draw this 6-membered ring in this form, write the carbon atoms. This is the second carbon atom to which OH is attached, which is above the plane. This is third, attached to fourth is methyl, which is above the plane. And 7th carbon atom, if this equatorial is above, this equatorial will be down, which is written here, and axial would be up. Like this, axial would be up. Then equatorial, again, if this is down, this will be up, down, and this way. So I have at the 7th position, I have this equatorial position, which is below the plane. So at the 7th carbon atom, I have shown the isopropanol group below the plane. Since this reaction follows a concerted mechanism in which a chair-like transition state is involved, hence I can say that this particular reaction occurs in such a way that I have methyl and OH groups which are above the plane and isopropanol group at the 7th carbon atom which is below the plane. So these are certain examples of Ene reaction. Remember, Ene reaction is a very fissile reaction, and particularly in the case of those systems where the enophiles are largely those systems which carbon has a heteroatom in it. So if it is a carbonyl group, carbonyl Ene reactions are very predominant in nature. These are very fissile. They are thermally permissible. Therefore, is a very common reaction to look out for while considering those systems in which both the Ene and enophiles are involved. Thank you so much for now. Perhaps with this we have winded up the pericyclic reactions.